Let's take a second and talk about significant figures, or as they're sometimes also called, significant digits. The issue with significant figures is that how we write the numbers is as important as the number itself. Because remember, for us, numbers aren't just numbers, they're data. So suppose I want to measure something using this ruler. It's graduated with inches with no smaller division. So each line on this ruler is 1 inch removed from its nearest neighbors. What's the limit on my accuracy? You might be tempted to say 1 inch, because of course there's only lines every 1 inch. But in fact, you can always estimate 1 decimal place more than you have lines. So in fact, the accuracy of this ruler is approximately 0.1 inches. And you can see this if I actually try to measure something. I'm now going to try to measure this blue block using my 1 inch ruler. Notice the edge of the blue block is more than 2 inches, but less than 3 inches. And so if I were to record it as simply 2 inches, I'm throwing away the knowledge I have that in fact my block extends past 2 inches. And if I were to write 3 inches, I'm essentially including what I know to be empty space as part of my measurement. So if I look, I can see that my block is not halfway between 2 and 3. In fact, it looks to be about 40% of the way from 2 to 3. And so it measures as 2.4 inches. Right? Now, that of course is not an exact measurement. No measurement is exact. But what I'm really trying to say is that it's not 2.3 inches and it's not 2.5 inches. So my 2.4 inches is reasonably accurate, at least to 2 significant figures. Each of those 2 digits is accurately known. The 2 is more accurately known than the 4, and this is always the case. The last digit is the one that has the most uncertainty. Another way of writing this is to say that the green block is 2.4 plus or minus 0.05 inches. Because of course, if the block was a little less than 2.35 inches, I would have rounded it down to 2.3. And if it was more than halfway between 2.4 and 2.5, I would have rounded it up to 2.5. So in fact, what I'm saying when I write 2.4 inches is that I know this object to be somewhat higher than 2.35 inches and somewhat lower than 2.45 inches. And so by writing the number this way, I not only indicate the magnitude of the number, I also indicate how accurately I know the number. 2.4 inches needs to be written as 2.4 inches if it's data, because it's important that only measured quantities be recorded. For numbers, 2.40 is exactly the same number as 2.400, because of course these zeros on the end don't change the number, they don't add any quantity to it. But for data, it implies measurement. Numbers that are written are measured. And so for actual data, I can't write those 3 numbers interchangeably. 2.4 is different than 2.40 is different than 2.400, because the accuracy with which those numbers would be measured is different. And so there's 2 or 3, depending on how you count them, rules for determining significant digits. The first rule is the easiest one. If it's not a 0, it is always significant, right? You would never write a 3 if you didn't know the number was a 3. If I have 12 of something, I wouldn't write it as 12.3 just to throw a number in the 10th place. I would either write it as 12 if I didn't know the number, or 12.0 if I did know the number, but I wouldn't just throw a 3 in there if I didn't actually measure it. So any number that's not a 0 is always significant. The second rule of significant digits is damn those zeros. Sometimes you need zeros even if you didn't measure the number. So sometimes zeros represent actual known information, and sometimes they're simply place markers. If you consider my weight of 200 pounds, how many sig figs is that? Well, in fact, it depends on how it was measured. It could be that I measured my weight to the nearest half pound, in which case all three of those digits are significant. It's also possible I did a coarser measurement. Right? I could have used a balance that only measures in 50-pound increments. So, for example, I stand on the balance and then someone puts 50-pound weights on the opposite side. And so clearly 5 50-pound weights is too much, right? And 3 is too few. And I didn't show the picture, but 4 is approximately balanced. But since I have coarse adjustment, I can only look at 50-pound increments. All I know is that I'm 200 plus or minus 50 pounds. So as a result, only one of those digits is significant, the 2. But I can't just write 2, because at 2 pounds, I'm a whole lot lighter than I was even at birth. I need the zeros to tell me where the decimal point is. And so this is what I mean by the zeros being problematic. Sometimes you need zeros just to mark position, even if you haven't actually measured the numbers. So there's really 3 kinds of zeros. There's leading zeros, zeros to the left of the first non-zero number. These are always irrelevant. They don't actually give me any information. All numbers have an infinite number of zeros to the left. If I weigh 10 pounds, well, for sure there's 0 100 pounds and 0 1,000 pounds and 0 million pounds. There's always a lot of zeros to the left, but they don't tell me anything in terms of actual information. So I never have to worry about leading zeros. If you've got zeros to the left of the first non-zero number, we just ignore them. They have no significance. Trailing zeros come in 2 different flavors. I have trailing zeros after a decimal point, such as in the 2 numbers shown here. And then I have trailing zeros that are before a decimal point. These are the ones that are more problematic. I guess we could also say there's a 4th kind of zero, which are zeros in the middle. But those are always significant because they're surrounded by significant digits on both sides. For my trailing zeros, if they're after the decimal point, they're also always significant, because I wouldn't need to write them if I didn't know them. These 3 zeros at the end don't do anything except tell me what's in that decimal position. They're not needed as place markers. That's different than the zeros before the decimal point. I need this 0 in 1,230, so I know it's not 123. I need all 3 of these zeros in 123,000, so I know the number is not 123. These are the ambiguous zeros. Sometimes they're significant, sometimes they're not. It depends on the measurement. Now, it's worth noting that, of course, as soon as I have a 0 that is significant after the decimal position, all the preceding zeros are also significant. Right? Everything between the first significant digit and the last significant digit is always significant. So the problem is the place markers. Sometimes I need zeros that aren't measured as place markers. The solution is to get rid of the place markers, and that's what scientific notation does for us. In fact, That's all scientific notation does for us. It's not an easier way to write a number. It's not a shorter way to write a number. All it does is remove the zeros as place markers. For example, if we go back to my 200-pound example, if I write it like I normally write numbers, I need the two zeros to indicate that the decimal point is actually here. But I can get around that by taking the decimal position and turning it into powers of 10. In fact, the 2 is clearly the first significant digit. All I need to know is where the decimal position is, and in fact it should be 2 positions to the right. So I incorporate that as powers of 10. What this tells me is that the actual decimal is 2 positions removed from where I'm writing in the number. All scientific notation has exactly the same form. It's a number followed by a decimal point, followed by as many other numbers that are significant. And so in my 200-pound example, if there's only one significant digit, I simply write the 2 followed by a decimal point with the 2 powers of 10 indicating where the decimal position should be. If 2 of those digits are significant, I write 2.0, again with a 10 to the first power indicating that I moved the decimal position 1 place, with again a 10 to the second to indicate that I've moved the decimal position 2 places to the left of where it originally was. And of course I could even have 3 or even more significant digits. And in all of these versions of the number, the accuracy is different because there's a different number of significant figures, but I don't have any zeros that are place markers because the place marking is all done by the powers of 10. So if I consider the following number, 0.0038340, again, all the non-zero numbers are automatically significant. The only real question is the zeros. In this case, I have 2 types of zeros. I have leading zeros, which are always irrelevant, and now I have a trailing zero, which is after the decimal point, so trailing zeros after the decimal point are always significant. So everything from the first 3 to the last 0 are significant. So this number has 5 significant figures. And if I want to write it in scientific notation, all scientific notation looks the same. I start with the first non-zero digit, immediately followed by a decimal point, and then I write any other significant digits. So in this case, to get the decimal point after the 3, I would have to move it 4 places to the right. And so I incorporate that move in the exponent as a negative, since I've moved it to the right rather than the left. And so I would write this number as 3.8340 times 10 to the minus 4 grams. The beauty of scientific notation is that only significant figures are written. Anything you see in scientific notation is significant because there's never a need to write something that's not. So if you see the number 1.200 times 10 to the 4th, right, because it's in scientific notation, all 4 of the digits in the prefix are significant. And the 10 to the 4th is simply the place marker. In the following number, 1.0205 times 10 to the minus 1, again, the prefix are all the significant digits, so there's 5 significant figures here, and the 10 to the minus 1 is simply the place marker. That's telling me that to get the decimal point after the 1, I had to move it 1 place to the right of where it started. So if I were to write it as a normal decimal, right, it would be 0.10205. No ambiguity ever remains. There's no need for zeros simply to indicate decimal position. And that's the only real advantage of scientific notation. How many significant figures in this number? Right, again, I ignore zeros to the left. The first non-zero digit is the 6. The final 0 is after the decimal position, so it's automatically significant. So everything from the 6 to the trailing 0 are significant, so there's 4 significant figures here. And again, if I wanted to write it in scientific notation, I start with the 6, followed immediately by the decimal point and all other significant digits, and then I include the decimal position as a power of 10, and again, since I went to the right 1, 2, 3 places, it's 10 to the minus 3.